Welcome! This is Paul Walcher. In this lecture, we're going to talk about logarithms. So this will be section 4.3 and 4.4. I like to take them together just because I really like a different organization than the one you get in the book. So we'll be moving back and forth quite a bit. So, logarithms. Logarithmic functions and laws of logarithms. Intro. We're going to start off talking about logarithms by talking about one of the big motivations. So every exponential function is one-to-one. If you graph them, and we graphed several last time, just taking a look at one of the basic ones. Let's say 2 to the x. If you look at the graph, well, even that graph would work, but zoom Z standard. That's a more typical set of axes. You can see it would pass the horizontal line test. It is one-to-one. Wherever I hit it with a horizontal line, I only hit it once. Therefore, it must have an inverse. But our previous methods for finding the inverse won't really work, because to find the inverse of y equals 2 to the x, we would interchange the variables, and then we would solve for y. But we have no method for getting the y out of the exponent as of yet. That's because we don't really have a mathematical way of expressing it. We can say what it is in words, y equals the exponent we put on 2 to get x. You may think that's belaboring the obvious, but honestly we have all sorts of things that express ideas like this in a small amount of time. I mean, our symbol for multiplication, if you tried to explain multiplication in words, it would take quite a few words. But if you just write the symbol that means it, you can express it in just a couple of symbols. Well, this is a case where we don't have a symbol to express this yet, so we create one. One of my professors in grad school, one of the first steps in solving any complicated problem is developing a notation with which to discuss it efficiently. Now, he was talking about complicated problems, but it scales down to smaller problems as well. For example, here we are introducing a notation to say specifically this. The exponent we put on 2 to get x, we use this notation, log base 2 of x. So let's deconstruct that notation. The log is short for logarithm, and that is just another word for exponent. So this means the exponent you put on 2 to get x. A is the base of the logarithm. It corresponds directly to the base of the inverse exponential function. So we were looking at 2 to the x, and we were trying to find the inverse of it. Well, the inverse of it is this, log base 2 of x. So the inverse of, say, 3 to the x, without doing the work, but I'll just spoil it for you, would be log base 3 of x. So there you go. And more complicated exponential functions will have more complicated inverses, but still, they're going to involve logarithms. The x doesn't really have a specific name that the book usually gives to it, but I usually give it the general name. It is the argument of the logarithm. And that's just easy to discuss. It makes it easier for discussion. So let's just mess with the notation some. Alright, let's look at some logarithms. Log base 2 of, let's say, 8. You might say, well, that's all very nice, but I'm going to tell you this is, in fact, an integer. It is a whole number. How, you might say? Well, think about what the notation means. The exponent I put on 2 to get 8. 8 is actually a power of 2. 8 is 2 to the third. So if I just told you, what exponent do I put on 2 to get 2 to the third, you'd probably just come right out and say, it's 3. And that's correct. The log base 2 of 8 equals 3. How about this? Log base 2 of 64. Might take you a bit longer to figure that one out, but that is actually log base 2 of 64 is actually 2 to the 6th. So this is going to be 6. How about this? Log base 3 of 9. What is the exponent you put on 3 to get 9? Well, that's 2, because 3 squared is 9. How about log base 3 of 27? Oh, that's 3. Log base 5 of 25 is 2. Sorry, my pen went crazy there for a second. Okay. We'll talk about how to find other values like log base 2 of 7, which is not a whole number, later. But for right now, let's stick with powers. How about the log base 2 of 1/8? Well, 1/8 is actually 2 to the negative 3. So that's actually going to be negative 3. Sorry, I actually had to reset my whiteboard program. It was giving me trouble. But log base 2 of, let's say, 0. Well, if you think about that, or I'll even say log base 5 of 0. There is no exponent you can put on 2 to get 0, because if you think about it, if I put a positive number on 2, I'll get 8 or something like that. If I put a negative number on 2, I'll still get a positive number, like 1/4, but it'll just be a small number. And if I put on 0, I don't get 0, I get 1. So there's no way I can get to 0 by putting an exponent on 2. That means this is undefined. It's actually only the second thing we've said that about in the entire semester. The other thing is dividing by 0. So this would be undefined as well. But you may have actually been able to generalize some of the properties of logarithms just by some of the work we've been doing. Also, if you look at, say, log base 2 of a negative number, for the same reason, I'll say negative 4, there's no exponent I can put on 2 and make it negative. So that would also be undefined. So that's actually a property. Logarithms are undefined when their arguments, T-H-E-I-R, and arguments are less than or equal 0. So one of the ways you'll be able to actually determine whether a logarithmic function has its domain, like say log base 3 of x minus 4. You just take the inside and set it greater than or equal to 0. And solve that inequality, and that would give you the domain of that logarithmic function. But you can also generalize another property, because the logarithms we've looked at so far, like the log base 3 of 3 to the third, we looked at the log base 5 of 5 to the 2, we looked at the log base 2 of several powers, but we start out with 2 to the third. That was 3. That was 3. That was 2. We also looked at like a log base 5 of 1, or 5 to the 0. And that was 0. You've probably already seen the pattern at this time. If you have the log base a of a to the x, with the exponent you put on a to get a to the x, is just always going to be x. That's actually a cancellation property that will be super nice when we're solving equations involving logarithms. So let's look at some of the properties of logarithms. So here's the one we just pointed out, log base a of a to the x equals x. But also, the other cancellation property, if you have 3 to the log base 3 of, let's just say something we know, 9. I know the log base 3 of 9 is 2, because the exponent you put on 3 to get 9 is 2. So that is 3 to the 2, which would be 9. But we should have known that without having to do this calculation. Because what does this thing mean? The exponent you put on 3 to get 9. And then I take that exponent and put it on 3. By definition, it has to be 9. Similarly, if I took 2 to the log base 2, and I'm going to put something that I can't calculate the logarithm for yet. Let's say 7. We don't know what the exponent I put on 2 to get 7 is, but I know if I take that exponent, the exponent I put on 2 to get 7, and put it on 2, I'll get 7. So, these are the first two properties, the cancellation properties, and they are very nice to work with. This is how your calculator can get by with only having a couple basic logarithms on it. And I'll come back to this. Right now, we're going to look at two very common logarithms that are on your calculator. And you can use them very quickly. So, base 10 logarithms. So that would be logarithms base 10. These logarithms are called common logarithms, and they're used often enough that we abbreviate the notation. So if I have the log base 10 of x, that is just written as the log of x. So for example, the log base 10 of 100 is written as just log of 100. It's written without the base listed. So if you see a logarithm with no base, that means it's base 10. It's not some problem that'll let you pick a base. No, no, no. If it's if no base is listed, it's a base 10. This, by the way, would be 2. So on your calculator, we have this log right there. So if you do log of 100, you get 2. And if you've ever wanted to know, say, what the exponent you put on 10 is to get 30, well, you just say log of 30. It's about 1.477. Let's check that. I'm going to round it off, so it's not going to be exact. But if I raise 10 to the 1.477 power, I do indeed get something that's very close to 30. That's what the notation means. That's what we should expect. Remember, log base 10 of 30 means the exponent you put on 10 to get 30. The exponent you put on the base to get the argument. The exponent you put on the base to get the argument. If you're having trouble, just kind of intone that as you're looking at logarithms. There's no need to get anxious or freeze up when you look at them. It's a simple operation. It's just a new notation, so you've never seen it before. Similarly to common logarithms are natural logarithms. Those are base E logarithms. They're just like these ones. They have an abbreviation. It's just instead of writing it without the base, we just change the log notation. It's Ln to indicate a log base E. And I just made a little note here. It's probably the most commonly used logarithm in higher mathematics. In fact, some calculators I've seen have no common logarithm and just have this. But if you wanted to, find the exponent you put on E to get 2, it'd be about 0.69. So let's check that. If I do E to the 0.69, what do I get? Something very close to 2. Now, those are the 2 logarithms that are on the basic calculator. I don't really need any more, though, because of this formula. This is called a change of base formula, and it says if you have a log base b of x, you can rewrite that as in terms of any other log base. So, for example, if I had a log base 2 of 7, I have log base 10s on my calculator, so I can rewrite it in terms of log base 10s. The way it goes is you have... Oh, that's a mistake. There, that's fixed now. You write the new log base of the argument, which in this case would be 7, over the new log base, log, of the base. So this would be log 7 over log 2. That would be the exponent you put on 2 to get 7. Now, we have an idea probably where this is. 2 to the 2 is 4, 2 to the 3 is 8. 7 is between 4 and 8. So the exponent you put on 2 to get 7 must be somewhere between 2 and 3. It's probably closer to 3 because, well, 7 is a lot closer to 8 than it is to 4. But let's see. If I look at the log of 7 divided by the log of 2, we get about 2.807. Let's check that. 2 to the 2.807 is very close to 7. And it would be even closer the more decimal points I put on. These are also irrational numbers. But note, I would get the exact same if I use a different base, like if I used base E. Ln over ln of 2. This is why old textbooks, before we had calculators that could do logarithms a lot, used to have tables of log values for log base 10, because you can calculate any other log base in terms of those. Your calculator will also probably have a function at the very bottom of the math menu called log base. L-O-G-B-A-S-E. That is a general logarithm function, and you're welcome to use it. But know how to use the change of base formula, because, well, for one, it's on the final, and it also pops up in the homework and in the, maybe, I'm not saying for sure, but maybe on the relevant test. So you at least need to know the form of how it works for those. But the upshot is that you can express any other logarithm in terms of e, or in terms of ln, or in terms of log. So if you have log base 7 of, I don't know, 10, well, you don't have to stop it there. You can actually get an approximation by just doing ln of 10 over ln of 7, or log of 10 over log of 7. Which in that case would probably be a simpler case, because log of 10 is just 1. The exponent you put on 10 to get 10. 1 over log 7. For the rest of these rules, product rule is a property for logarithms that will be helpful in simplification. This just says if you have a logarithm that has a multiplication inside, like for example the log base 2 of 10. Well, log base 2 of 2 times 5, so that's the log base 2 of 2 plus the log base, that's a t, plus the log base 2 of 5. Product rule says you can break it up like that, and that would be 1 plus the log base 2 of 5. Why is that useful? Well, it's useful in separating out variables. Sometimes you'll have like 10x. I'll just do a straight base 10 log. And sometimes you might want to separate the x out inside its own logarithm. Log of 10 plus log of x. Like so. That would also simplify to 1. And you can do something similar with quotients. So if you had 5xy over 2z, that would be log of 5xy minus log of 2z. And you could expand it further using product rule if you wanted. See? Because 5xy, that would be a log 5 plus a log x plus a log y, and then log 2z minus, for parentheses, because I'm splitting up that into 2 terms, minus log 2 plus log z. So altogether, log 5 plus log x plus log y minus log 2 minus log 3. But, oh, sorry, z, not 3. So, a quick rule of thumb if you're doing a problem where it says expand as far as you can go, is anything on the bottom is going to have a negative sign. Anything on the top is going to have a positive sign. So 5 was positive, x was positive, y was positive, 2 was negative, and so was z. This kind of thing is very artificial. We're probably not going to be doing an actual application that involves this in this much detail, but it's just practice messing with the new notation. because, like I say, it's a completely new thing for you guys, so you need to practice what you can do with it. We will use these rules, but just not to this degree. Speaking of degrees, that's a nice segue. The last rule, and by the way, these three are called the laws of logarithms. They have names. Product rule. They're kind of the named ones. Change of base formula is named as well, but it's not really a rule, just so much as a formula. But a product rule, quotient rule, power rule is actually based on the product rule, and it is very useful in solving equations because it says if you have, I'll do a base on this one, log base 3 of 5 to the x minus 1. If you have an exponent on your entire argument, you can factor out that exponent in front. That is exceptionally useful. So, a very simple one would be log base 2 of 7 to the 4th would be the same thing as 4 log base 2 of 7. If you have an exponent on the entire argument, you can pull it out. Now note, this does not mean log base 2 of, let's say, 3x to the 4th. That is not equal 4 log base 2 of 3x. Because the 4 was only on the x, not on the entire argument. It would have to be like this before you could pull the 4 out. In that case, yes, that would be equal. A very common mistake when dealing with logarithms is assuming something like this. Log of, say, 5 over 2 equals log of 5 over log of 2. But that is not true. This is how you deal with a quotient. It becomes the log base 5 minus, it becomes the log of 5 minus the log of 2, not the division. Logarithms do not distribute across a division or a multiplication. It just seems easier to see that for a multiplication for some reason. So, don't distribute logarithms. They don't do it. Alright, let's do some examples. First we're going to look at is exercise 10. This has the log base 2 of 160 minus log base 2 of 5. And the key here is that you can do this without moving to your calculator, because we know by the quotient rule that if I have a subtraction of two logarithms with the same base, I can write it as a division, 160 over 5. Let's see, 160 over 5 would be 32. Log base 2 of 32. Then, log base 2 of 32, that is log base 2 of 2 to the 5th. So that's just going to be 5. How about this one? Log is a base 10 log, so I'm not going to write a base. 1 over the square root of 1,000. Let's see here. 1,000 is 10 to the 3rd. So that's the log of 1 over the square root of 10 to the 3rd. Then, if you recall, a square root is a 1/2 power. So this is log of 1 over 10 to the 3rd to the 1/2. Then, if you recall one of our laws of exponents, if you have something raised to an exponent raised to another exponent, you multiply it. So that's log of 1 over 10 to the 3 halves. And then lastly, An exponent on the bottom is just a negative exponent. So that's 10 to the negative 3/2. Why did I write it as a power of 10? Well, that's because this is a base 10 logarithm. And the exponent you put on 10 to get 10 to the negative 3/2, or just use that first property of logarithms we looked at, is just going to be negative 3/2. And we're good. That's not the only way to approach this. You could have, say, done log 1 minus log of square root 1,000. Log of 1 is just 0. And then work with this. 10 to the third, 10 to the 3/2, and then we got 3/2, but then you got a negative in front of it. And you get to come out with the same thing. Alright, how about 18? Here's the log base 2 of 8 to the 33rd power. Well, 8 is a power of 2. So this will be the log base 2 of 2 to the 3rd to the 33rd. And then remember, when you have an exponential expression raised to an exponent, you multiply. So that'll be 2 to the 99th, which will just be 99. Now, the instruction here is expand using the laws of logarithms. Well, let's take a look then. Here's 23. We have log base 2 of x times x minus 1. Didn't actually mean to draw that so far down. But if we're going to expand this out, we want to write as many different log expressions as possible. So log base 2 of x by the product rule, because I've got a multiplication here, x times x minus 1. So plus log base 2 of x minus 1. How about 31? Could go a lot of different routes on this one. Log base 2 of xy in parentheses to the 10th. Alright, you could distribute the 10 through x to the 10th, y to the 10th, break it up with the product rule, x log base 2 of x to the 10th plus log base 2 of the y to the 10th, and then use the power rule to bring out the exponents. I think I'm going to do this first. I'm going to use the power rule first, bring out the 10, log base 2 of xy. Then I'm going to use the product rule in this part. 10 times the log base 2 of x plus the log base 2 of y. And then we'll just distribute and be done. 10 log base 2 of x plus log base 2 of y. Nope. 10 log base 2 of y. Forgot to distribute. Oh well. Then here's a very typical problem. I often put something like this on a quiz, if not on a test. Log of x cubed, y to the 4th, over z to the 6th. And you may actually remember from our discussion on the PowerPoints, you may guess where this is going. We're going to have the top ones are going to have positive signs, the bottom one's going to have a negative sign, and we'll bring out the coefficients as well. And you can feel free to jump there. But I will go step by step. So I'll do quotient rule first. Log of x cubed y to the fourth minus log, and it is a base 10 log of z to the sixth. Now that first one I can split up into two logs with the other one, the product rule. X cubed plus log y to the fourth minus log z to the sixth. And the last step would just be bring out those coefficients. So 3 log of x plus 4 log of y minus 6 log of z. You might guess where the next instruction is going to go. We are now going to combine. The exact opposite. They're going to give us expressions like this and combine into a single log expression. I'm going to abbreviate logarithm as, or logarithmic as log. Let's start off with exercise 50. Here we've got 3 log base 2 of a plus 5 log base 2 of b minus 2 log base 2 log base 2 of c. Well, just like here, you can actually jump pretty quickly on this one. I mean, here you saw we ended up with 3 log of x, 4 log y, minus z, 6 log z. You can pretty well jump straight from here to the end. Well, same thing here, you can probably jump. But I will go straight through it. I mean, the first thing you want to do is take the coefficients and put them back in as exponents. Because remember, the properties here don't have coefficients in front of these. So you need to get rid of those first. Well, that's easy enough. Log base 2 of a cubed plus log base 2 of b to the fifth minus log base 2 of c squared. Now, everything is positive is going to be on the top. So, log base 2 of a cubed b to the fifth. Everything that's negative, straight on the bottom, over c squared. Something like 59. Use calculator and change a base formula to evaluate. Well, let's say log of 7 of 2.61 what they're saying here is use ln or log on your calculator to calculate it. So let's just say ln of 2.61 over ln of 7. They want it rounded to 6 decimal places. Oh, let's do that calculation. Then we only have a couple more things left in the section. So ln of 2.61, ln of 2.61 divided by ln of 7. About 0.493008. So that is what we would put .493008. Well, the other things we have left in the section are the exponential and logarithmic forms of an equation. This will really become obsolete once we study solving equations in 4.5. So you might just want to move straight on to 4.5 rather than look at this. But this is just a way of moving an equation between exponential and logarithmic forms. So, for example, if I had, say, y equals 7 to the x. Well, the logarithmic form of that equation would be the log base 7 of y equals x. And both of these equations convey the exact same information, they're just different forms. And one of them might be easier to solve than others. Because it might tell you it wants you to solve for x. Well, you'd put it in logarithmic form and you'd solve for x. Solve for y, it's this. So this is just a diagram for moving between them. You notice the base of the logarithm is the base of the exponential. The y, you have an exponent. Logarithm is an exponent equals y, so that's the exponent. And then the other part is that, the x, the argument, that goes on the other side of the equal sign. I think it's really of limited usefulness, but you're welcome to memorize it if you want. The book does go over it, and honestly most books do, so it's probably of some value. And the last thing for the section, a logarithmic function with base a is this. F of x equals log base a of x. Remember, a logarithm was undefined for arguments that were 0 or negative. So the domain of a logarithmic function like this always has to be 0 to infinity, not inclusive, which are greater than 0. Notice also it has the same restrictions on its base as we had for exponential functions. That's not a coincidence, because remember we set these up to be inverses of exponential functions. If you look at the graph of one of these, it basically looks like the inverse of an exponential function, where an exponential function has a horizontal asymptote, a logarithmic function has a vertical asymptote. So let's look at a graph or two. If you look at, say, log x, base 10x, and look at the graph, yeah, it has a vertical asymptote at 0, because it's undefined there. And it goes off to infinity. Range is all real numbers. It does go up very slowly, but it does go up infinitely. If you wanted to, say, do a log base 2 of x, if you have the log base function in your math menu, you can use that. But I'm just going to use the change of base formula, because remember, log base 2 of x I can write as ln of x over ln of 2. So I'll just do that. ln of x divided by ln of 2. And there's log base 2 of x. So like if I plug in 4 into that, let's see, I don't want that one, I want that one. If I use trace and I plug in 4 for log base x, I do end up with 2, because the exponent you put on 2 to get 4 is 2. If I plug in 8, I get 3, because the exponent you put on 2 to get 8 is 3. So yeah, graphing it, that's the real reason they give you the exponential and logarithmic form, really. As far as graphing, if you had it's probably easier to build a point table in the exponential form, which would be 2 to the y equals x, because then you don't have to do any kind of crazy manipulation. You can just say, well, plug in for y. Y is 1, 2, 2, 4, 3, 8, 0, 1, negative 1, 1/2, etc. That's probably what most of my students use it for. Although most of my students, if they're graphing a logarithmic function, they will just plug it in the calculator and use the point table. Just don't forget about that very useful feature of your calculator. It will make point tables for you. It's just second graph. There you go. 2 to the x's. Oh, sorry. Log base 2 of x is here. Log base 2 of log 10 of x is here. So there we go. That is logarithmic functions. Already through. Next time we're going to start doing the fun stuff where we actually solve exponential and logarithmic equations. So for that we will get just a little bit more theory, really just two solving principles, and then from there and the properties we've already got, we'll be able to solve both types of equations. Equations involving logarithms and equations involving exponential pieces. And that'll really be all the theory for the section. The last section of the chapter is just applications, so there's no new theory there. It's just using the solving methods we've already gotten to solve word problems, application problems. So I will talk to you then.